Hello dear students, welcome to the fourth session of the first unit of Mass Transfer 2 course, that is extraction. So hope all of you can remember whatever we learnt in the last classes, the last three sessions. So let us continue that discussion today. So this is what you studied in the last class. So last class was meant for a discussion on ternary systems and how the composition of these ternary systems can be represented on a triangular diagrams. So what is the significance of triangular charts and how they are constructed, how they are used in liquid extraction operation. So all that we discussed in the last class. So with that, um, these are the things that we are supposed to understand in today's session. So first, we are going to discuss about the selection of a suitable solvent for liquid extraction. That is how you can select a right type of a solvent to carry out the particular liquid extraction operation. And after that, we are going to take up the starting part of the extraction equipments in which we are going to see the classification of the various extraction equipments. Okay. So selection of solvent for extraction. See, whenever you are given a task of separating the components of a liquid mixture using extraction operation, the first thing what you need to do is you have to select a suitable solvent that can dissolve a particular component that needs to be separated from the original solution that you have. So that selection of solvent is not easy. So because you need to select a suitable liquid phase that can dissolve the particular component and also has certain characteristics so which are required to carry out the operation in a most economical and safer manner. So in fact you will come across a number of solvent that can dissolve a particular component, and out of those solvents, again by considering what are other characteristics present in a given solvent, you need to make a suitable choice. So solvent phase selection extraction ಅಲ್ಲಿ ತುಂಬಾ important. Solvent ಅಂದ್ರೆ it is uh, that liquid phase which is used for dissolving solute from the original solution. So let us now see what are all the characteristics that you need to consider to select a solvent for extraction. So any particular liquid phase that can be thought of as the one suitable for extraction will not possess all the properties that are required for extraction. So a compromise is to be made for selecting the best out of the a number of choices available. So you may not expect the very good characteristics in all the solvents. So by considering in which characteristic a particular solvent is good, and you need to make a suitable judgment while selecting one solvent out of a number of choices available. So the following discussion in which you're going to learn about the properties or the characteristics of the solvent for extraction, you will understand how we can make that best choice. Okay? Let us see what are all these properties. The first one is selectivity. So we already have learned what is meant by selectivity in the beginning class. So the ratio of concentration ratio of solute to feed solvent in extract phase to that in raffinate phase is called selectivity, also as a separation factor. So it is the measure of effectiveness of a solvent for separating the constituents. So selectivity indicates the degree of separation possible by extraction. So this ratio for a particular solvent is need to be calculated. So by knowing its value. It should be always greater than 1, just like your relative volatility in distillation. So first that is considered, and higher values of selectivity is considered as the requirement for the extraction. So selectivity value, if it is higher, then extraction is carried out using that particular solvent. So if the selectivity for any solvent is equal to 1, then it means that separation of the given liquid by using the particular solvent in extraction is not at all possible. So that is how selectivity helps in choosing a solvent for a given operation. So next comes the recoverability. See, we all have learned that after extraction is done, the solvent will be recovered for reuse by distillation. So how easily a solvent can be recovered decides whether it is a best solvent or a not that good one. So recoverability is also very important after the selectivity. So a solvent is usually recovered using distillation operation. So we expect that the solvent selected uh, should form a solution with the solute liquid, which can be easily separated from that solute liquid using distillation. Means the relative volatility of that solution should be very high. So that is the requirement, second important requirement of a solvent. A solvent should be recovered for reuse frequently by distillation. Hence, it should not form an azeotrope with the extracted solute. And for low cost recovery, relative volatility should have been like that actually. The relative volatility of the solution components in the given solution of solute and solvent should be high. So that is how it makes the operation less costly. So if it is not forming an azeotrope, or if it is forming a solution of having high relative volatility, then that is the right kind of solvent for the given operation, so that it can be easily recovered without um, much expenditure and can be used as a suitable solvent. So also the latent heat of vaporization of solvent should be low whenever it is to be volatilized. So distillation always involves vaporization of the mixture. So that vaporization, if it is to be done with the solvent, then it is required that the amount of latent heat of vaporization is lesser. So that is all about recoverability. So we'll discuss the third characteristic. Uh, just a minute. Sorry for the interruption. So let us now understand the third important characteristic, so called the distribution coefficient. We also have learned the definition of distribution coefficient in the first class. So hope you can remember it. A distribution coefficient is nothing but the concentration ratio of solute in extract to the raffinate to that in the raffinate phase at equilibrium. So it is usually denoted by capital K. So the equation form of this definition is K is equal to Ce divided by Cr. So Ce is the concentration of solute in extract phase. Cr represent the concentration of solute in the raffinate phase, both measured at equilibrium. So when this ratio is having higher values, that means the given solvent is capable of extracting more amount of solute. It is its extraction capacity will be higher. So higher values of distribution coefficient for a given solvent is necessary to select that particular solvent as an extractant in the given operation. So that is how we need to understand how we can make a best choice by considering selectivity, recoverability, and distribution coefficient. So these three are the important factors. So apart from these three, there are other factors also, such as density, the fourth characteristic. So the whenever a solvent is added to feed solution, since it's immiscible, it will stand as a separate layer. If it is having higher density, it will be at the bottom of the vessel, and if it is having a lower density, it will be a top layer in the given vessel or the equipment. The difference in the densities of the two liquid phases at the end of the operation, saturated liquid phases means the phases which are resulted by the end of the operation, should be larger for physical separation. Okay, so if the two layers that separate out after the extraction is over are having higher density differences, so that is the best solvent for the operation. So because the higher density differences help in easy physical separation of the two resulting phases. So that is how the density of the solvent is also playing a major role in the selection of solvent. So coming to the solubility, okay, usually the solvent will be insoluble in the feed solvent. Okay? So to what extent that insolubility is required? Okay, the solvent insoluble in the original solvent or the feed solvent should be preferred. That means whichever solvent that you are selecting should have a as less solubility as possible in the original liquid solvent or the feed solvent. So that way we can make the operation more economical. That means the extraction capability will be higher if it is less soluble in the feed solvent. So also it is the one we should be having high solubility for the solute. So the solute in the operation should have a high solubility towards the selected solvent, and the solvent selected should have a least soluble, less solubility towards the feed solvent. That is the solubility factor that should be considered while selecting a solvent. So if this condition is satisfied, then amount of solvent required for the given degree of separation will be lesser. So less amount of solvent means less expenditure to be spent on the operation. So that way insolubility also is a very important factor in selecting a solvent. So next comes IFG in short, which is known as interfacial tension. So interfacial tension between the two immiscible phases also is important. If it is high, then coalescence of the emulsions occur more readily. Say during the operation, when the solvent is added to original solution, to establish a maximum contact, one phase will be dispersed in another phase by agitation. So when you disperse the phase, what you get is emulsion. So means one of the liquid phase will be disintegrated in the form of droplets into the another phase, which is a continuous phase. So that emulsion after the transfer, means the distribution of the components is over, have to again coalesce. Coalescence means the dispersed phase will again become a separate continuous phase. So that coalescence of the emulsions, separation of the two phases as a two separate continuous phases should occur more readily. So for that, you require that interfacial tension to be high. So this is again a very important thing than even the dispersion. So dispersion ಆಗೋದಕ್ಕಿಂತನೂ emulsion, that is coalescence ಆಗೋದು ತುಂಬಾ ಇಂಪಾರ್ಟೆಂಟ್. ಎರಡು ಫೇಸ್ ಸಪರೇಟ್ ಆಗಬೇಕು ಅಂದ್ರೆ at the end of the operation. So interfacial tension or the IFT should be very high for the given system of solvent and solution. So now some of the miscellaneous characteristics need to be considered. So the solvent selected should be chemically stable and inert towards the other components. Means it should not be chemically reacting with the other components of the system or the operation. And it should not also be corrosive towards the common materials of construction. So if it is corrosive in nature, then you have to go for a very costly construction using a corrosion resistant materials. In that way, the fixed cost for the operation will become high. To reduce that cost, the solvent selected should not be chemically reactive and also should not be corrosive. So next comes the cost factor. If you have a number of solvents having the same kind of characteristics, then you have to go for a solvent that is cheaper. So cost also comes into picture, is important, should be considered at this point. The solvent should be non-toxic, non-flammable. Flammability should be less. It should be non-poisonous in nature. Also, a solvent is required to have a low viscosity. It should not be very thick liquid. So that affects its handling and flowing ability. So it should not have a high freezing point because due to temperature variations it might solidify in the operation. So low freezing point is required. Low vapor pressure is also very important because if it is having high vapor pressure, so whenever there is a temperature rise, the solvent may get vaporized and it will be wasted. So to avoid that, the solvent should have a low vapor pressure. So these characteristics are important from the point of view of handling and storage of the solvent in the plant. So that is all about the selection of solvent for extraction. Okay, so now let us briefly discuss about the extraction equipments. So today we will understand its classification so that in the next class onwards we can discuss the different extraction equipments in detail. So liquid extraction is one operation where you require to construct a equipment that brings two liquid phases into intimate contact so that a proper kind of mass transfer occur between them. And after that, the phases need to be separated. So keeping in mind all these aspects, you need to design a suitable equipment. Okay, so like in any other operation, here also an extraction operation can be carried out in a batch-wise manner or a continuous manner. So accordingly, we have batch type extractors and continuous extractor. So based on the mode of operation, you have two types of extractors, the batch extractors and the continuous extractors. So whenever we're dealing with simple systems and you are handling less quantities of liquids, you have to go for batch operated extraction equipments. On the other hand, when you want to handle large quantities of liquids, I mean, if it is a large scale operation of extraction, then you have to go for a continuous operation, continuous several contact operation. So this is how we can select a batch extractor or a continuous extractor. So however, based on the type of operation that is involved, most of the extraction equipments are operated continuously because in most of the cases it's a large scale operation carried out in a industry. So here the continuous operation may be successive stage-wise contact operation or a differential contact operation. So accordingly, we have two types of extractors. One is a stage type extractor, another one is continuous contact or differential contact extractors. So examples for stage type extractors are mixer settler, plate columns or tray columns, pulsed sieve plate column. This is a variation or a modification of plate column. So such kind of extractors are stage type extractors in which the extraction operation is carried out in a stage-wise contact manner. Then you have the second category called the differential extractors. So the examples of differential extractors are packed column, spray column, pulsed packed column, rotating disc contactor, etc. So these are the equipments in which the two faces are contacted in a continuous contact. That is, throughout the equipment, they will be in the continuous contact with each other. So stage type extractors are the one in which the two phases are allowed to mix together so as to reach equilibrium, and then they are separated before being passed countercurrent to each other. So there will be a number of stages involved in the equipment. So on each stage the two phases are allowed to come into contact, that is they are mixed together, and once the equilibrium is reached they are separated and again passed to the successive stages, usually in a countercurrent fashion. So that is how basically the stage type extractors operate. So the advantages of stage type extractors is the simplicity of design. The design is relatively simple. These have less amount of axial mixing. Axial mixing taking place is less. It is mixing along the axis. High stage efficiency. These will have quite high extraction efficiency compared to the continuous contact extractors. So coming to the drawback, the extraction equipments coming under stage type extractors are large and bulky. So comparatively, they are large in size and also bulky units because they require a separator after every stage. So that reason makes them large units, so requiring a large floor space. That is the only drawback with the stage type extractors. Coming to differential type extractors, so as I said already, the two phases will always be in continuous contact throughout the equipment. So these will be compact for a given throughput and require small floor space. As I said, so there is no physical separation of the phases uh, frequently inside the equipment. So they are compact for a given throughput and also they require small floor space comparatively. So this is another way of classification of extraction equipments. So some extraction equipments um, involve in dispersion of the phases and the flow of phases produced by the gravitational force. In some extraction equipments, the flow of phases and the dispersion. Both are flow of phases may be produced by the gravity, but the dispersion will be produced by the mechanical agitation. So in case of plate column, packed column and spray column, the phase interdispersion, it is two liquid phases will be dispersed into one another. That dispersion and the flow through the equipment will be produced by the gravitational force that acts on the density difference between the phases. Whereas in case of other type of extractors like mixer, settler, rotating disc contactor, the dispersion of the phases will be produced by the mechanical agitation. Means some kind of agitation mechanism is used to disperse one phase into another, and the flow will be produced by the gravitational force as before. So this is how we can identify the different types of equipments used for extraction operation. So that discussion will end now. So let us now go through the multiple choice questions. So dash is the measure of effectiveness of solvent for separating the constituents. So in extraction, so is it the relative volatility? Is it the distribution coefficient? Is it the selectivity? Is it none of these? So measure of the degree of separation is usually given by the selectivity. So option C is the right answer for this question. If selectivity is dash, separation by extraction is not possible. So let us look at the options. 1, greater than 1, less than 1, 0. So if we can go back and recall what you learned in the session, it is understood that selectivity, when it becomes unity, then separation by extraction is not at all possible, because unity selectivity means both the equilibrium phases will have the same quantity of solute, same ratio of the solute to feed solvent. So that means you cannot separate the given mixture by using the particular solvent. So if selectivity is 1, extraction is not possible. Answer is A. Selectivity should be dash for separation to be possible by liquid extraction. So you require selectivity to be greater than 1. Okay. So out of the 4 options, it is the first option that is the right choice. Higher values of distribution coefficient means dash will be the amount of solvent required for the given duty. Is it higher? Is it lesser? Is it none of this? So higher values of distribution coefficient indicates that the amount of solvent required will be lesser. So distribution coefficient with a higher value indicates that we can use less amount of solvent for the given duty. In extraction, interfacial tension should be high. So you require that interfacial tension should be high because dispersion of the phases occur more readily, easy flow of phases, coalescence of emulsions to occur more readily, none of the above. See, interfacial tension, if it is high, then the coalescence of the emulsions will occur more readily. So that is the reason why we require that IFT should be high. So option C is the right answer. Rotating disc contactor is a dash type extractor. Is it a stage-wise contact type extractor? Is it a continuous contact extractor? Is it a batch operated extractor? Is it none of the above options? So RDC is a special type of extractor in which continuous contact is established. So it is not a stage-wise contact equipment. It is not a batch operated one. So the right option is option B. So let me take leave now. So with that, so today you understood how you can select a suitable solvent for liquid extraction operation. What are the characteristics that you need to consider, and by you need to make a suitable judgment to select a best solvent. And later on, we also understood how we can classify the extraction equipments, what are the different categories, and what are the types of equipments coming under each category. From the next class onwards, we will be taking up the different extraction equipments to study their construction, working, and other important aspects. So thank you for joining me once again. See you in the next session.